Okay, let's talk about now adaptive controls. And today's topic, I would like to give a big overview first, and then talk about one specific algorithm based on pole placement, a simple but really powerful control structure. A few reasons to do this that are easy to understand now are there will be cases where you don't know the plant that you are controlling, or the plant that you're controlling simply is changing and you need to update your control to accommodate these changes. And then there will be scenarios where even if your plant is working fine, but there is substantial disturbance you may know something about the disturbance. You may know it's a drift, it's a constant, but you don't know exactly what are those parameters of this disturbance. And then they can also change as well. In these scenarios, adaptation is usually the best way to do. And in general, there are two steps to do adaptive control. One is you need to pick a control structure first. And then based on that structure, design your adaptation algorithm. So here, our structure today will be on pole placement. And then after you design the structure, there will be, again, two different general scope to do adaptive control. Usually, if we know the model of the plant, we do model-based design. So the controller will be designed based on parameters of the model. And if in this case, the plant parameters are unknown or time varying, then we can identify this on the fly first, so we can learn theta first, and then use theta to update the controller. A different approach is we update, so the theta parameter that we update are directly the parameters of the controller. And the plant parameters are not directly updated. Both these algorithms are possible, so these two, we will see their implementations in this algorithm, in this controller structure on pole placement. So today, let's talk about the pole placement structure for adaptive controls. Here. So let's talk about this. So this is called RST structure for pole placement. Suppose we have a plant that has a few steps of delays. This time we don't limit, D can be 1 or it can be more. The RST structure is slightly different from our conventional single control block diagram structure. It has a few components inside. It looks like this. There are these feedback components. There's also this feed-forward component inside. That will help shape the input, let's call it R, into the feedback block. And let's call this R star. And then the output, let's call it Y. So that's the structure. We can analyze a few things. First of all, let's talk about the transfer function, the closed loop transfer function from here to here. This is not difficult. It's going to be feed-forward pass multiplication and then divided by 1 plus the overall loop transfer function. So if you carry out the computation, it's going to be this. All right, and then the direct pass from here to here is 1 over S Q B and A. And it equals, in the denominator, AQ SQ plus Q B R. And then numerator is Q negative D B Q inverse. That is the transfer function from R to Y. Pole placement works on this part. Pole placement starts from here. All right? So the pole placement happens by working on this polynomial. So we design closed loop characteristic polynomial to be, let's call it D. So let's design it this way. This, I have a few more terms than what we have seen before, but at the essence, this is a polynomial equation. This is a Diophantine equation, actually. So this is known. This is from the plant. This is what we need to design. This is what we assign. So this is indeed nothing but this is a Diophantine equation. And we know immediately the solution concept from our previous discussions. It has if the orders of these polynomials are assigned properly, then it will be guaranteed to have a solution if these two are coprime, if the plant is irreducible. This can be solved by matching the coefficients. And solution guaranteed. If plant is irreducible. So that's the general concept. But let's be careful. Let's just be rigorous and provide all the orders of these polynomials. Let's say the order of the polynomial B is B0, it's M as usual. and B0 is not 0. In other words, we have factored out all the delays, and this leading coefficient is not 0. Otherwise, we're going to have an actual step delay that we need to factor out into D. So m's order B, and then A is n's order. So let's write down, this is n's order. This is D plus M. All right. In general, the way to design these is try to start with something simple. So in here, if I look at this system block diagram, if the plant has stable zeros, then a good way to start with the design is to cancel these stable elements by S, and that will lead us to some simplifications immediately. So this is pole placement with stable zeros. Let's say the principal goal is to cancel B in SQ if they are cancelable. We'll talk about the case when this can't be done. We cannot have unstable pole zero cancellation in general. So let's cancel this B, and then let's say I may have some other design considerations. So I'm going to introduce a lower order S, I call it S prime, to introduce other features. So if you have B in S, then you can see there will be a common term from the left-hand side. D will naturally contain a BQ inverse inside. And then we can play around the other close to poles by assigning a D prime based on the performance goals. These would lead us to substitute this inside and then cancel B on left and right. We're going to get AQ S prime plus Q negative D R and D prime. So the Diophantine equation has been simplified substantially. The orders are, this is n's order, this is D's order. And we need to match the orders. So let's design S prime and R such that the orders are D minus 1 and then n minus 1. And then on the right-hand side, it's going to be n plus D minus 1. We talked about solutions, scenarios where the Diophantine equation will have guaranteed solution. If you revisit that theorem, it will say this A and Q negative D, they are co-prime. And then the orders of these polynomials are not, obviously, if you keep these orders to be very, very high, then it won't be possible to solve a single unique solution. But if you keep these orders at the minimum required, then it will have a guaranteed solution. So in other words, let's now specify these coefficients now once we know this order. So S prime is 1 S1 Q inverse to SD minus 1 prime Q inverse D minus 1. And then R is R0, R1, Rn minus 1. Right? That will be the design. With these, the transfer function, closed loop transfer function, will be substantially simplified. You can see this B cancels with this B, and our S contains the B term is also going to be canceled. The result is very simple. Q negative D in the numerator. In the denominator is going to be A S prime plus Q negative D R, and it equals. So we have placed the closed loop poles by designing this to be D prime. That's pole placement. So this means now this means the output. Let's now use the time domain result of the design. So this means yk equals q negative d, d prime, and rk, because this is the transfer function from r to y, so in time domain this is the implication. And this means d prime q inverse y k plus d equals rk. All right? I have shifted the advanced operator, shifted the delay operator to the left, and becomes yk plus d. Okay, so we finished this part of analysis. Let's now go back to here and take a look at what kind of feed-forward controller we want to design to make the output to track this desired reference. So now the feed-forward pass. T, and then the closed loop. Now I'm going to simplify this to use the designed overall transfer function. So how can we design this and the reference signal here to achieve, so our goal, let's say, is we have a desired output, and we want the actual output to track this desired output. We know D prime, this is stable, all right? So what would be some very simple design to simplify the whole thing? If it's stable, then we can cancel. So let's design T to be D prime. Which will give us R star K going through a delay operator becomes the output Y. And if this is just a delay operator, then the ideal way for R star is going to be R star we're going to design it to be YD. I can't just use directly YDK because I'm going to have a delay operator here. So instead, if I know my desired references, I can advance it and have YDK plus D. This will cancel with this delay operator and give us the goal. So that's the feed-forward path of design. That's the design principle. Now, in reality, we need to be just a little bit careful when doing this. So in reality is what will happen. Now I'm going to write this down. So in reality, this is not really exactly this portion because you have to implement this in reality. Okay? So in reality, this is not really everything combined together. You can just implement delay operator. You have to run this through this operator and then go through this closed loop dynamics. So in reality, let's call this RK again. What we have is actually this. So RK is D and YD from the left side. And RK is also D prime Q inverse YK plus D from the right-hand side. Okay, so treat this in two ways. On the left is D prime YD, and on the right is D prime operate on Y, and then there's a delay element. I'm going to add it into here. So there's a subtle significance in recognizing this, because this means the true design result is D prime Q and Y minus Y D is 0. All right? In reality, there's always some kind of transient. You don't usually directly get, you start with Y equal to YD, start with K at 0. There's usually always some kind of transient. And this equation actually characterizes that transient. So this is a slightly, I'll come up with a example then to illustrate the significance. So let's do one example to understand a little bit of these conclusions. Let's say G is and then 1 minus A0Q A1. Let's just do as simple as possible. This is the plant. So D equal to 1 and B equal to 1. And it's clearly a scenario. So we're essentially at here. Okay? So B is 1, already canceled, or already don't need to worry about it. And then the orders will be N is 1. So let's design S prime. N is 1. M is 0. So S prime should be designed to be 1 plus, and this is 1, right? And then R is R0, right? That's the design from the right-hand side. And then the closed loop transfer function GR to Y is Q negative D. I'm going to write AQ S prime plus R all right, so this is the transfer function from R to Y, and it equals 1 plus R0 minus 1 Q inverse. So we can see that this very simple pole placement design, it can arbitrarily shift my closed loop poles by this mechanism here. That's the tuning of R0. So this effectively gives us, this is our D prime. And let's take a look at the entire picture. Our T is equal to D prime. So our D is 1 plus R0 minus 1 Q inverse. And then goes through, this becomes RK, and goes through the closed loop transfer function. Generate Y. All right. This is the picture. Let's say we have some initial condition where Y0, let's say it's at 10. And then let's say R star, our desired goal is to make the system to track a constant from an initial position of 10 to go to 1. Let's see our design, how it makes the convergence happen. So R star K, from our analysis, this should be YD K plus D. Should be YD K plus 1. D is 1. All right, so it should be always 1 from the constant reference design. From here, we can know RK, it equals this T operating on R star K. So it is R star K plus R0 minus 1 R star K minus 1. And we can write it as YD K plus 1 plus R0 minus 1 YDK by substituting R star equal to YDK plus 1 in here. And then on this side, we have YD and R relationship. We know that YK and R relationship. YK is closed loop transfer function operating on RK. So YK plus R0 minus 1 YK minus 1 will be rk minus 1. Let's run some numbers and see how the convergence happen. So let's see. Y0 is 10, starts with 10. And Y1 is equal to negative R0 minus 1 Y0 from this side plus R0. Right? And it equals, let's plug in the numbers. Y0 is 10, and R0 is on this side. So let's see, R0 is YD1 plus R0 minus 1 YD0. So far, so good? All right? So it's going to equal to 1 plus R0 minus 1 based on our design goal. And it equals negative 9 R0 minus 1 plus 1. So you can see by tuning this R from the controller side, we can control the convergence speed of the output. So let's say we design R0 to be 0.5. Then we are going to get 1 minus 9 times negative 0.5. And it equals 5.5. All right? So crunch these numbers and you can see some trend now. Y is actually from 10 is becoming closer to 1. And what is the extreme convergence speed? How can we design, what kind of boundary values we can choose for R0 to make the convergence as fast as possible? Right, is if we design the closed loop pole to be 0, then we can have the convergence to be 1. One-step convergence. All right? So from this step, we can already see Y is going through a process to converge to. You can continue and calculate Y2, etc. But the key message is that Y doesn't directly goes to YD. It has to go through a convergence condition. But if you compute this, our equation on the right-hand side, if you compute this, this is going to equal to, this is our D prime, 1 minus R0, 1 plus R0, Q inverse. And then YK plus D. So in our scenario, it would YK plus 1 minus YDK plus 1. If you compute this, you can see actually this is always 0. Okay, so this means, let's say K equal to 0. Let's check that condition. It's going to become 1 plus R0 minus 1. I'm going to multiply things out. So this multiplied with YK first is going to become Y 1 plus R0 minus 1 Y0 because of this delay operator minus YD1 plus R0 minus 1 YD0. All right, so take a look. Plug in these numbers in here. We know Y0 and Y1 already. Let's say R0 is 0.5 in that example. You can see this is going to become 5.5 plus negative 0.5 times 10 minus 1 plus negative 0.5, 1. Anyone quick with numbers can see this is going to give us 5.5 minus 5 is going to become 0.5. 0.5 minus 1 minus 0.5 is 0. All right? So, conclusion. You don't get directly, there is a transient, and that transient is characterized by this polynomial actually. It's characterized by how you design your closed-loop poles. All right? And the extreme case you can design the closed-loop pole is to make the closed-loop pole to be at 0 in the discrete time case. So now, we have this important equation now. This will become our design goal. Remember, now from here, in system identification, this is what we have. We have a Planck output. And then we have an estimated Planck output. We want to update our parameter vectors, such that this will converge to Y. All right? So that's our design goal in there. And then in adaptive control, what we have is D prime YK plus D we have a desired reference we want to track. And the principle of our adaptive control should be, this is the ideal case, it's going to match. And then in reality, if it doesn't match, we're going to design the adaptation such that this will converge to that. And then in system ID, this is how we characterize the regressor vector. We parameterize the plant, the process, with phi times theta. And then what we're going to do next is to parameterize this thing such that this becomes a new phi vector times a regressor vector. I will write it actually here. So what we want to do is to parameterize as regressor times a unknown coefficient theta. So that's what we're going to do next. So it's about time. That's for today. Okay, so I'll see you next time.